Okay, good afternoon, everybody. Okay, you must have got from section.
So your voice is breaking.
Is it
No, sir.
is it okay now?
Yes, sir.
Okay. Okay, guys. So all of you must have got notification from your institute that some classes may be started in hybrid mode. Okay. I wanted to know like how many people you are, are here already. So can you just write in the comment that if you are on campus, just write in comment that you are, okay? You just write yes, so if you are on campus, so you can just answer me. So if you are here, you just write yes. Yeah. I just want to see how many people are here, and accordingly we can also think about. Yeah. Yeah. Okay. Yeah. So far we looked at the 2D heat transfer problem, and we had to obtain the weak formulation of that. So we did some work already. Yeah. Okay. So what we had to get was, if you start since the beginning, what we have done so far. So looking at, so we had this strong form, then multiplied by W, which is a function of XY. And then we had to do the integration by part. So first we looked at this one, number one, and then we had a number two. So number one we sorted out, W times divergence of K times gradient of T integrated over the whole domain. This we worked out, and we found out that I is nothing, or 1 is nothing but this value. So this is I only, right? So this one is I. So I is equal to this value we got, and then we have the number 2 as well. Yeah. So what we have as the 1 plus 2 is equal to 0 is the actual equation, and hence from 1 what we get is, you have here, so this is the closed loop integral over the whole boundary. So we have W, okay, so W times K, okay, W times K gradient of T, okay, dot N, yeah, and D gamma then minus we have this gradient of, say, so gradient of W dot K gradient of T d omega. So this is number 1 plus number 2, which is W, yeah, and then we have S x y. W is also function of x y, so this and d omega all equal to 0. So the whole thing is what is the weak form. Yeah, now we have to solve the problem. So this is the weak formulation. Now we have to assume, remember that K del T we can also write as Q is equal to K del T, right? K delta T, and we can also write in general, instead of writing this in general, we can write the weak form will be as WQ, see here, this is WQ dot N d gamma, okay, then omega, then we have del dot so sorry, we will have Q, not, no, you don't write like this one, it will be just Q here, okay, so this will be just Q here, okay, just Q d omega. So you have del W dot, this is Q only, dot Q, so we have just dot Q only, then plus omega, and then W S x y d omega equal to 0. So you can write just W also instead of writing K del T, so you can write that way also. Okay, so in general, you can also derive like this one only, instead of writing K del T was not required. And when you have general, then you can also have as an isotropic material as well, right? So the same thing, like the notation we had, like Q, this tilde is equal to, as you know, that we write Qx and Qy, yeah, and similarly N tilde, you can write it as Nx and Ny, right? So in vector form, or sorry, in matrix form also you can write, right? So in matrix form also you can write like this, matrix form, matrix, so this, right? Then you have WQ dot N, so that simply means W, so we write W first, and then Q is like this, so this will be Q transpose, so Q tilde transpose N tilde D, like, so you can write like this. Then we have this, so we can also define del tilde as del over del x, del over del y, like this one, yeah. So so we can write accordingly, this minus omega, and then gradient of W, which will be del transpose of W, right? So this, and then we have to multiply it by multiplied by Q dot Q, so we have simply Q tilde, right, d omega plus, and this will be just simply W and S xy d omega equal to 0. So in matrix form also you can write this way. Yeah. So anyway, these are the this is the weak form, and next thing what you do, you assume some value, and what do you have to solve here? Here you can also write where Q bar T, or you can write as, sorry, the not Q bar was Q tilde is equal to, either you can write this is minus K, right, minus K del T, right? This is so you have minus K, here delta, so you write delta and then you write T. Yeah, so this is like this, or this is for isotropic material, peak material. Otherwise, an isotropic Q tilde will be equal to minus, and you have D here. D is a matrix, and then you have this. Yeah, so this is also there, that you know. So this is general purpose you can write in matrix form. Say if the isotropic material, this will be simply this, and isotropic material, you put this and solve it. So anyway, so given this, now next thing is how to solve the problem. And solving the problem means that you have to assume some value, right? So let's solve for isotropic case. For isotropic, you know that we have this case. Yeah, so we can take that, we can solve accordingly. Yeah, so so we write in vector format only, so that is much easier to do work on that. So first of all, we whatever we solve, if you look at the in vector format, this value, and for isotropic material or this is the one, right? This is the in vector format. So we have this equation, let's call this is number 3, equation number 3, right? So this is the one we want to solve it, and in order to work on it, we have to find out this T is the variable, so we have to find out T, and you see you have also W value here. Yeah, so isotropic case, so we are going to work on this equation. Which equation? This W del okay, I think we also look at the sign, guys. Yeah, here has to be minus. Okay, so this is minus here, so accordingly we have to put that. Okay, so yeah, so you put Q equal to minus, so this here you have to write minus Q everywhere. So this will be minus, this will be plus, and so on we have to write. Okay, so you have to be careful with that. So this we are going to write minus here, and we write plus here. Okay, this is because of this Q equal to minus, sorry. So wherever we have K del T, we write minus Q here. So this becomes minus, here we get plus. The rest remains the same. Okay, so here we write minus, here we write plus. Okay. 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 So coming back to the the original equation that we have to solve. So this we write K W T dot N D comma, okay, then we have minus mega dot K T d omega plus S W S X Y d omega equal to 0. Now we have to solve the problem. This problem there may be subject to some boundary conditions. So let us say this is the domain and this is the gamma is the boundary. Okay, now what happens that this we have to calculate on the boundary. You go through a positive direction which is anti-clockwise, go like this, you have to integrate that, and then you have this thing, yeah, that you have to calculate over this whole domain. This also you have to calculate the whole domain. There may be some boundary conditions, something given that there may be some two kinds of boundary condition, right? As you know, there may be some temperature given. So let us say T given, right? Temperature is given here, or you call it essential boundary condition, essential boundary condition, and let us say you call it gamma 1 or gamma T, right? Gamma T, where temperature is given, okay, and wherever temperature is not given, you have to give the Q, yeah, let's call it gamma Q, yeah, and this is what you call it the natural boundary condition. Natural boundary condition is given here, means Q is given, that means Q is given, right? Okay, so this is the basically what it means is total gamma has two parts, gamma T and gamma Q. Yeah, so this is union of both of them. So you can write like that. Yeah. So the boundary conditions typically will be given as, yeah, so it will be given like T at gamma T is equal to T naught, let us say, example, right? And T at there may be given like Q dot N, which is equal to Q bar equal to Q dot N at gamma Q is equal to, let us say, Q naught given, right? So this kind of boundary condition will be given. Accordingly, you have to work with it. Yeah. Any question? Yeah. Okay. Okay. Now we will now look at the kind of like a domain which can be, if you have a domain like this one, you can fill it with what is known as the triangular element. Triangular element. Yeah. So that means you can have element like this. You can have right. You can make element like this, right? So you can make an element like this, triangular element. In order to solve that problem, you can discretize the domain into triangular element. Okay, so if that is the case, then maybe we are talking about a very small problem, for example, right? You can have, or let's say this is the whole domain. You have partitioned with the triangular elements, and if you look at the one element like this, right, and we have node number 1, 2, 3. So we arbitrary one we chose. Let us say we chose this one. Yeah, so we have 1, 2, 3. Yeah, and it may have the coordinates x1, y1, x2, y2, x3, y3. Yeah, okay. Now, for the three, let us say, as you know that if you know how, if you can formulate for one element, you can element for, you can formulate for all of them, means you can solve the problem. So you first, what you do, you have divided into a number of elements, you number the element now 3, 4, 5, 6, 7, 8, 9, 10, like that, right? 11, 12, 13, 14. You have made 14 elements. So you are taking arbitrarily the nth element. This is the nth element. This is the nth element you are looking at, and you want to solve the problem. Now, if let us say temperature at element 1 is T1, at is T2, node 1 is T1, node 2 is T2, node 3 is T3, then how does the temperature varies within it? Just like in 1D, here in 2D also we write like Tx, Txy, sorry, Txy is equal to, right, summation of Ni, of course it will be a function of x and y both, Ti, where I varies 1, 2, 3, y, there are 3 nodes now. So it will vary like this, right? Okay, where Ni we have to find out. Only thing is what is Nixy? And you know that what should be the property, that there will be 3 of them. Property, you know, property always summation of I equal to 1 to 3 has to be equal to 1, right? Or N1 plus N2 plus N3 is equal to 1, right? That you know. There are various ways of doing the same thing. Yeah, so you can have, in order to find out that, either you can formulate, you can say Ni xy is equal to alpha I. So there is something called Pascal triangle. Okay, Pascal triangle. What is that? Here you have, it gives you the ideas which all terms you can have. So let us say you have 1, then you have x, y, then you have x square, xy, y square, then you have x cube, then x square y, right? Then x y square, then y cube. So these are the terms, which term you can have in the shape function. So in this case, we have n1 xy is equal to, you see, 1 xy. You want 3 term, right? Because there are three nodes. That means you have 3 equations, and that means there has to be 3 terms. So 3 terms. So we will choose this. Yeah. So we are going to use alpha I plus beta I. So this is Ni equal to beta I x plus gamma I y. Yeah. We can choose like this one, and then we solve, then we can have these conditions. What? Say n1 x1 y1 is equal to 1. N1 x2 y2 equal to 0, and N1 x3 y3 equal to 0. So you know that a property Same property you have to write that n1 will be 1 here, 0 here, 0 here, right? In 1D also we did the same thing. So n1 at node number 1 is 1, at node number 2 is 0. So similarly here, n1 is 1 at node 1, n1 is 0 at node 2, n1 is 0 at node 3, and hence this is how it is, right? Okay, and hence you can write that, and since this is alpha, you can write automatically in this case that alpha 1, right, plus beta 1 x1 plus gamma 1 y1 is equal to 1. Alpha 1 plus beta 1 x2 plus gamma 1 y2 equal to 0. Alpha 1 plus beta 1 x3 plus gamma 1 y3 is equal to 0. Or you can write it as like this: 1 x1 y1, 1 x2 y2, 1 x3 y3, right? And then you have alpha 1 beta 1 gamma 1 is equal to 1 0 0, and you can find out this by inverting this, right? Yeah, so that tells you that the simply, right? So you can write alpha 1 beta 1 gamma 1 is equal to, and then you have 1 x1 y1, 1 x2 y2, 1 x3 y3, inverse of that, and then 1 0 0. You can find out this, and similarly you can find out all other values, right? So similarly you can find out similarly alpha 2 beta 2 gamma 2 is equal to 1 x1 y1, 1 x2 y2, 1 x3 y3, inverse of that 0 1 0, and alpha 3 beta 3 gamma 3 is equal to 1 x1 y1, 1 x2 y2, 1 x3 y3, inverse of that 0 0 1. Yeah, so you can do that, but this takes a lot of time. So luckily we have a better way of doing it. Yeah, so you can do it, but let us say you put it like that. Okay, so and after that what happens? We will have we put in like the original equation. Also W, the way you have wxy also formulated the same way. You say this is ni xy times wi, right? So where I equal to 1 to 3 in this case. Yeah, so finally if you put this if you put these values if the in the original equation, then what do you get? So we will get this. You can write it as, how do you write it? You write n, you can write n1 n2 n3, and you have w1 w2 w3, right? Similarly you write txy, also you write as n1 n2 n3, which is a function of xy is equal to t1 t2 t3. You can write like that. Yeah, okay. Now this equation, if you look at the original equation, right, so we can put that there, and you get the values. So now you are going to use what? You are going to use this del t, right? You are going to use del t in that case, right? Del t, which will be equal to what? So we are going to use del t, which will be equal to this will be equal to, you are going to have this till the, right, and then temperature of that, multiplied by temperature, and so how do you write? This will be equal to del over del x, del over del y, right? And then you have this n1, n, n2, n3, and then you have this t1, t2, t3. Now, how do you multiply this? You will have 1, sorry. This is a 2 by 1, this is 1 by 3. So there will be 2 by 3 matrix, right? So this, if you have to write this one, this is, if you want, we have that this one in the equation, original equation, right? So basically we are going to write this is equal to, here you see this is the first one, 1 1 1 2 1 3, right? Then 2 1 2 2 2 3. Got it? So basically this will be simply n1 x del n2 x del n3 x del n2 x del n, sorry, n1 y, n2 y del n3 del y. Okay. And then you have t1, t2, t3. And this we also call a B matrix. This is a B matrix times T matrix. So del T is nothing but this. Yeah. Okay. So regarding the original equation, not to forget, we are going to put these values there. Yeah, and we have to write this equation there. I mean, we have to put whatever we got here. So we have this multiplied by this and so on. Accordingly, we have to put those values. So so looking at the matrix form, so we have this. So both are equivalent basically. This and both are equivalent. So you see that we have like these terms. So we have this term, this del, whatever you calculated multiplied by k will give you this one. Yeah. So whatever all the values we have to calculate and we have to put. So only thing is here, this is a little bit complicated because of the this is 2D problem. So and you have to write in a particular way so that the meaning is also conveyed, right? So so gradient of T we write like this, right? So similarly gradient of the gradient of W also we have to calculate, right? And finally this will turn out as B and this is W. Means whatever the B is, where W is equal to W1, W2, W3, it will be W1, W2, W3. It goes like that. Yeah. Okay. Okay. So given these values, let's now put in the original equation. And original equation, if we have here, you remember we wrote it like this. So I will repeat again and again the weak formulation so that we don't forget also. So we had W Q dot N D gamma we had write that minus we had omega, and then we had of W dot Q dot, right? And then we had plus omega W and S d omega is equal to 0. We can also write that uh, matrix form because to use it, right? So we write the same.
Sir, your voice is breaking in between.
So hold on, guys. Fine now?
Yes, sir, it's now fine.
Yeah, okay.
Here.
Can you hear me now, guys?
Yes, sir. It's fine.
Still there is some problem.
It's perfectly fine.
Okay. It will be slow though. Okay. So let's. So I'm going to switch off my camera in case it helps. Okay. Okay. So we have to write in matrix form as we have done earlier. So we can write as we did earlier. So minus, then we have W. So W, we know that here straight away we can write W here. Anyway, whatever the value of W on the boundary that we have to apply, say we will write a W, that's it, because and then we have Q dot N, so let it be here, because typically we these things are given on the boundary, so that's why we'll put like this only. Okay, so let it we write like this. We will mix it basically. We'll mix this with this anyway. These are a scalar value. These are all a scalar, so we can mix. So this will be plus only because I have not changed anything. Here I'm going to change from Q to minus K gradient of T. So we'll write plus in that case here. And then we have gradient of W. So gradient of W. So we have that. See, B and W. So we write BW, but BW. And what you see here is this is B is, so this will be gradient W is nothing but this will be 2, this is 2 by 3, this is 2 by 3, this is 3 by 1, so 2 by 1, so this is 2 by 1, right? So 2 by 1, but you know that both are dot product. Finally it has to be in the scalar form. So this BW, basically this will be transpose of that, because we are going to dots, that's why it is like that, right? And this one is K del T, so we'll write K here. K is anyway constant, so I will take it out, K outside. And then Q is nothing but K times minus K times del T, the gradient of T. So minus, we have made plus because of that. So this is nothing but we have derived already this B times T, right? And we have D like this. Yeah. And then plus we have we have this W and S. Yeah. So W and S, W, as you know, is nothing but N, right? So the N times, so we have transpose of that and W, and then S, X, Y, D, where, so this is equal to 0, where N is nothing but N1, N2, N3. So N transpose will be like this one. And yeah, sorry, the N times, yeah, fine. So, and this is W1, W2, W3. So multiplied by this is basically what the W is. So you get like this one. Yeah. You guys, any problem? So this one is N, so this will be N1, N2, N3, then W1, W2, W3, both multiplied together, and it will be like that. Okay, now this we can also write it as W transpose N as well, right? So we can also write this, so basically this N transpose W is equal to W transpose N. You can also write like that. So anyway, this is a scalar, it will come a scalar, right? So you can write like that. So so this one, if you see the second term, let's we call it this term number 1, 2, 3. All the three have three significance. Okay, so let's call it the integral A, integral B, or integral C. Okay, so integral 1 will be from the boundary condition, whatever the boundary condition is there. So we can write basically this one, this, yeah. So we can write IB equal to minus IA minus IC. So this is equal to minus this. Yeah. Okay. So what we get is, from here we get something like this: K times T is equal to some force, or we are used to K times U equal to F. We get that type of thing. So just to see where we are leading to, from first the integral, that not first IB, let us say the second one we're talking about, this, let's simplify. This term, which is right now is K, then you have for the whole domain, and then we have a transpose of that, right? So we get a W transpose, B transpose, then B, then see this. So W transpose B, then T times T and d omega, right? Which is equal to K W transpose, then K omega, and then we have B transpose B omega, and then you have T, right? So which is equal to basically nothing but whatever our K is, yeah, and then we have W1, W2, W3, and here we have T1, T2, T3, yeah, which is equal to, we get, we have W multiplied here, and we have K and multiplied by T here. So this second integral is like this. Now look at the IA. This one is, we can simplify it. So IA is equal to, we have closed loop integral of W Q dot N and D gamma. Now if we have, you know that we have two types of gammas, right? So we have the gamma T and gamma Q. So this we can write is equal to gamma T W Q bar N bar D gamma plus, okay, here we don't have to put the closed because we are writing both, and then we have gamma of Q and W Q dot N with D gamma is equal to, now we know that temperature is given here, that means W will not be given there, means W will be 0 there. Now it will be given, but value will be 0. So W will be 0. Here T is given, T equal to T naught, so W will be 0 here. So for first one, value will be 0 simply, is equal to 0 plus, why? Because W will be 0 at this, yeah, plus, and at this point, as per the original, we what is given? Given is Q dot N is given to be Q naught, right? So here the value will be equal to we have W Q bar, yeah, Q bar or equal to Q naught is given, W Q naught is given here already, yeah. So finally this will be equal to gamma Q. So this is equal to gamma Q W Q naught d gamma. Yeah. So whatever the value is, you do it, and which will be in terms of W1 value as well, depending on the N1, N2, N3, whatever will be there, and you put those value inside that and you will get that. So this will also you get in terms of W only. W1, W2, W3. Now the third part, if you see, so C is equal to what you have, omega, and then we have W xy, and then you have S xy d omega, right? Okay, so is equal to W is nothing, as we can write also, which will be equal to the W1, W2, W3, right? Omega, and then you have N1, N2, N3, right? So 1 by 3, 3 by 1, so this is W, right? Then you have S, X, S, X, Y, d omega, right? So which will give you in a form of W1, W2, W3, and there are some force terms, right? So F S1, F S2, F S3, S for the source term, right? So this will give you the force vector from here, and this is W1, W2. Meaning that whatever you see here is basically, this is equation, this all equation you can change into this form, and finally this will be in this form, because there will be W term here, W1, W2, and because as you know that W1, W2, W3 are arbitrary, finally you get these values, right? So basically what you see here is, this is nothing but this multiplied by this, and this is the stiffness matrix basically. Yeah. So your stiffness matrix is nothing but, from here we find out that K is equal to small k is the conductivity, whole omega, and then what you have, B tilde temp and B d omega. So if you calculate this one, you can get the stiffness matrix. Force vector from the source one, this is the force one, right? And for the boundary, you have to evaluate what exactly the values are. So you have right now W coming, but W itself will have W1, W2, W3. Yeah, so finally, basically, you can find out the K times U equal to F term. Finally, what I mean to say is, if you simplify, you will get W transpose, yeah, then K times K tilde T is equal to W transpose F. You will get something like this. Since W is arbitrary, sorry, this is transpose, here also transpose. So if W is arbitrary, you can automatically get K times this equal to F. Yeah, where F will have component because of the source, and also because of the boundary fluxes and temperature as well. No? Okay, any question, guys? More when we solve the problem, you will understand more. Okay, so we have to solve the problem. This just gives you overview for the 2D problem, how to go about it. So this N, looking at, we took N1, N2, N3, it could be N1, N2, N3, N4 if it is 4 noded, and so on. So in general, it tells you that a stiffness matrix you calculate like this one, K equal to K, then this B transpose B d omega. Force you can, how you find out? Force is, this gives you the force. More we will do when we have solved the problems. Okay. Okay, guys.
Hello,
Thank
sir.
you. Yeah.
Sir, maybe it is somewhere irrelevant, but I wanted to ask question. Even in continuum mechanics, we prefer triangular element over others. Even in this class, we prefer triangular element. Sir, what could be the reason? Whether it will reduce, give the accurate solution, or it will reduce the our complexity?
In continuum mechanics, you have triangular element.
Yes, sir. Yes, sir.
In continuum mechanics, you don't have element, man.
Sir, for analysis, we preferred triangular elements, sir.
In continuum mechanics, you do not have any triangular element. There is no concept of element there.
Sir, in deriving Cauchy stress formula, we preferred triangular element over other elements.
No. This element, that element is different. Okay. This element is different, that is different. That is for, this is continuum mechanics, but this is just opposite of that. Here we are looking at all the discrete system. We are converting from the continuum to discrete system.
Yes, sir. Yes, sir. I could understand that.
Yeah. So here we are not preferring or anything. So it is just one of them. Next time we will have 4 noded element as well. Yeah. So if it is 2D, how many options do you have? Either you will have triangular or you will have quadrilateral, right?
Yes,
So two types. You can also have like 5 noded, all kind of things, So but the simple geometry is either triangular or quadrilateral. Those are simple geometries. Yeah, and within that geometry, the number of nodes can be different. So number of nodes could be, for triangular only, you can have 6 noded as well. See, you can have like this, 6 noded, or you can have quadrilateral with 5 nodes like this. So we will look at all those things later on. We will do all kind of things we will do.
Sir, in the Pascal's triangle, how did you decide to take only one and xy?
The rule of thumb is you start from 1. The top one you have to take it.
No, sir. I mean, like you only went till linear terms.
Right.
Like,
Why you are asking?
sir, I'm asking because x
No.
square.
No, you are asking me why. Why we took only 3? That
Yes, sir.
Right. Okay. So let me go back where we did. Just a minute. So here. So first of all, there's only 3 nodes, right? So you have 3 nodes, yeah. And we start with the simplest form first. Means we have to make the order as low as possible, right? So if only 3, because there are 3 nodes only. 3 nodes means 3 equations, right? If there are only 3 equations, that really means we can have only 3 factors, only 3 coefficient and constants, right?
Sir, so like if we have a quadrilateral, then how will we take?
Then you have to keep it symmetric, right? So then you will take 1 x y. You cannot be x square, otherwise it will not be symmetric. So you will take this. So you will take
okay,
like this.
okay.
So you have to
Sir.
make symmetry.
Okay, sir. Got it.
Yeah. In some cases, if you have 5, for example, then you don't know what to do. So you can then you can miss this one. Then you can have this x square, then this. So that way, sometimes it works. You have to look. You have to take. Then you see whether it's working or not. Then you can change. But try to make it symmetric. If the element is symmetric. If element is not symmetric, then there will be then let us say you have node something like this, triangular only, and you have something like this one. Then it's not symmetric, right? This is not symmetric. Then you will 4 noded. So it will be something like this, right? But if you have which is right in the middle, then you know that it has to be this, and so on. Yeah.
Okay, sir.
So you will do more later on. Right now we are just making it look like as if it is 1D only. There's not much different. Only thing is notations. Because of that, it sounds difficult, but without notation you cannot actually solve the problem also. Yeah, so it's easy only. When we do a lot of solve problems, we will see that it becomes more easy and easy. Any other question, guys? Okay, so I somehow I could not. Okay, maybe I will get some email in which your comments yes no will be there. So, but in any case, I will discuss more on starting the classes in offline mode. Okay, so I will talk to you later for those who are on campus right now. Okay, guys. Okay, see you tomorrow. See you on Wednesday. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.